Nuclear fission occurs when a nucleus of an atom is split into two separate atoms when hit by a neutron. The most common isotopes to undergo nuclear fission include uranium-235 and plutonium-239. Uranium, the element, was discovered and named by German chemist Martin Klaproth in 1789. Uranium was named after the planet Uranus, and in fact, the discovery of uranium was what made the discovery of radioactivity possible.
Radioactivity is the emission of particles from disintegration of atomic nuclei.
But nuclear fission itself wasn't successfully conducted until 1934 by Italian scientist Enrico Fermi. At that time, he did not realize what was occurring in the atom. It wasn't until 1938 when physicists Lise Meitner and Otto Frisch realized that the nucleus of the atom was being split, and named the process nuclear fission, after the biological process of fission during cell reproduction.
After lots of experimentation, it was determined possible to predict the fission fragments that fly apart with a large release of energy.
The discovery of this process ushered in the atomic age. Soon atomic bombs were being constructed in America during World War II as a result of the Manhattan Project approved by President Franklin Roosevelt. The end product of this project were two fission bombs. The Little Boy dropped on Hiroshima, Japan on August 6, 1945, and the Fat Man detonated above Nagasaki, Japan just 3 days later. Since then, nuclear fission has been used to generate electricity in nuclear power plants, but not without risks, as seen in cases such as Chernobyl, 3 Mile Island, and Fukushima.
In the nucleus of an atom, the actual mass of the nucleus is less than that of its neutron and proton components. The difference between this actual mass and component mass is called the mass defect. For example, a helium atom containing 2 neutrons and 2 protons, or nucleons, has an atomic mass about 0.8% lower than that of 4 hydrogen atoms, each containing 1 nucleon. The missing mass is equivalent to the energy of the formation of the nucleus, as based on Einstein's E equals mc squared equation, and is a measure of the total binding energy of the nucleus. The binding energy is the amount of energy required to separate a particle from a system of particles. In this case, binding energy refers to nuclear binding energy, or the energy required to separate an atomic nucleus completely into its different protons and neutrons. A larger binding energy equates to a more stable nucleus, as it is more difficult to separate such a nucleus into its constituent parts. The largest binding energy, or the highest stability, occurs near the mass number 56. Heavier nuclei, therefore, will try to split into 2 lighter nuclei to become more stable.
Binding energy, or the minimum amount of energy required to overcome the forces holding an atom together, is later referred to as barrier energy.
The binding energy creates an attractive nuclear force, holding the components of the nucleus bonded together. At the same time, the protons, with their equivalent positive charges, are repelling each other. This results in a surface tension in the nucleus, reduced by its spherical formation. If the nucleus is excited in any way, however, it begins to move, causing deformations in its spherical shape. The surface tension steadily increases, and the nucleus moves towards its maximum potential energy. This is called the saddle point, as based on the shape of the nucleus at this point. From there, the repulsive forces between the protons drive the nucleus to further separation until the potential energy drops completely and the nucleus is split in 2. This drop in potential energy results in an increase in kinetic energy, sending the 2 new nuclei off in opposite directions and constituting the massive energy of nuclear fission. Any difference between the mass of the original nucleus and that of the 2 products is converted into energy, again as based on the E equals mc squared equation. Nuclear fission results in 2 new nuclei, as well as radioactive products and excess neutrons. These neutrons can induce fission in nearby nuclei and create a chain reaction.
Want to hear a fun fact? More than 70% of America's emission-free power comes from nuclear energy sources. To better understand the concept of nuclear fission, the 2 main types of fission must be understood: artificial and natural. Natural fission occurs spontaneously in nature without any stimulus, while artificial fission is not spontaneous and needs to be induced by some form of energy greater than or equal to of the barrier energy. Based on the graph of binding energy per nucleon, elements that have atomic mass units over 130 and undergo nuclear fission are considered natural because of the spontaneous fission that occurs. These elements are so large that fission will occur naturally and result in multiple isotopes with much more stable nuclei. For example, uranium-238 undergoes spontaneous or natural fission with a half-life of 10 to the 16th years. To quicken this process, energy can be induced. As energy is induced, it no longer is called natural fission. It is now artificial. Like stated earlier, artificial fission is ignited by some source of energy greater than or equal to that of the barrier energy within the nucleus of the element itself. Insufficient amounts of energy added to the element requires more kinetic energy from an outside source if artificial fission is desired.
One of the most iconic examples of nuclear fission includes the two atomic bombs developed by scientists in the United States, Little Boy and Fat Man. These bombs were built during the Manhattan Project during World War II, a secret government project approved by President Franklin Roosevelt in response to fears that Germany had already been building or possibly successfully built an atomic bomb. As it turns out, these bombs were dropped onto cities of Japan on the orders of President Harry Truman and were credited with ending the war.
Want to hear a fun fact? There is one Japanese man in the whole world to survive both Hiroshima and Nagasaki bombings.
Since then, a new kind of bomb has been developed, the hydrogen bomb, which relies on fusion techniques instead of fission. They are named so because of the use of hydrogen gas in combination with uranium atoms. Fusion bombs are more powerful as they utilize energy from uranium atoms more effectively. Nuclear fission has many benefits and is a very powerful process.